Look at this color, this brilliant, vibrant blue. It's not a natural mineral. It's not ground from stone. It's not extracted from plants. It's synthetic, man-made, created in a furnace. 5,000 years ago. This is Egyptian blue, the world's first synthetic pigment. The ancient Egyptians invented it around 3000 BCE, used it for over 3,000 years. Then the formula was lost. For 2,000 years, nobody knew how to make it. Until the 1800s, when chemists finally recreated it. But here's what's remarkable. Here's what we just discovered. Egyptian blue has quantum properties. Properties we didn't even understand until the 21st century. The ancient Egyptians created a material with quantum mechanical behaviors. Without knowing about quantum physics, without understanding electrons or photons or energy states, they just knew it was beautiful and useful. Welcome to the chemistry of ancient Egypt. Let's start with what Egyptian blue actually is. Walk through any major museum with Egyptian artifacts. The British Museum, the Louvre, the Metropolitan Museum of Art. You'll see this blue everywhere. On tomb walls, on statues, on ceramics, on jewelry, on sarcophagi. King Tutankhamun's burial mask, that brilliant blue and gold, Egyptian blue. The ceiling of the temple at Dendera, painted as the night sky, Egyptian blue. Cleopatra's palace decorations, Egyptian blue. This wasn't rare. This wasn't reserved for royalty. Egyptian blue was ubiquitous, common, used extensively throughout Egyptian society, from monumental architecture to everyday pottery. But what is it? Chemically, Egyptian blue is calcium copper silicate. The formula CaCuSi₄O₁₀. That's calcium, copper, silicon, and oxygen, combined in specific ratios, heated to specific temperatures. The result, a brilliant blue pigment, stable, durable, light-fast. It doesn't fade, it doesn't degrade. 5,000-year-old Egyptian blue looks as vibrant today as when it was created. The color itself is distinctive. Not quite ultramarine, not quite cerulean, not quite turquoise. A unique blue, bright but not harsh, vivid but not overwhelming. Under normal light, it's stunning. Under ultraviolet light, it glows. Egyptian blue is luminescent. It absorbs UV light and re-emits it in the visible spectrum. This property makes it useful for modern authentication. Museums use UV light to verify Egyptian blue on artifacts. If it glows, it's real. But the ancient Egyptians didn't know about UV light. They didn't understand luminescence. They didn't have ultraviolet lamps. They just knew this blue was special, beautiful, permanent, divine. The Egyptians associated blue with the heavens, with the Nile, with life and fertility. Blue represented creation, rebirth, eternity. So they invented a way to create it. Creating Egyptian blue wasn't simple. This wasn't grinding minerals. This wasn't extracting dyes. This was chemistry, high-temperature synthesis, the first synthetic pigment in human history. The recipe requires 4 ingredients: calcium, typically from limestone or calcium carbonate; copper, from copper minerals like malachite or azurite, or from bronze; silica, from sand or crushed quartz; natron, a naturally occurring salt used as a flux. These ingredients had to be ground finely and mixed in precise ratios. The exact ratios matter. Too much copper, wrong shade. Too little silica, doesn't form properly. The ancient Egyptians developed the correct formula through experimentation, trial and error, observation, refinement. Then comes the heat. The mixture must be heated to between 800 and 1000 degrees Celsius. That's 1500 to 1800 degrees Fahrenheit. At these temperatures, the ingredients undergo a chemical reaction, a solid-state synthesis. The calcium, copper, and silica fuse, molecular bonds form, crystal structures develop. The result? Calcium-copper tetrasilicate, Egyptian blue. This requires specialized furnaces, not cooking fires, not pottery kilns. Purpose-built furnaces capable of reaching and maintaining these temperatures for extended periods. The ancient Egyptians built such furnaces, designed specifically for pigment production. Archaeological evidence shows specialized workshops, dedicated facilities. This was industrial-scale production, not artisan craft. Egyptian blue was manufactured in quantity, distributed throughout Egypt. The process wasn't secret. Multiple workshops produced it. The technology was widespread, but it required knowledge, skill, resources. You needed access to raw materials, fuel for the furnaces, technical expertise. The resulting pigment came in different forms, sometimes as solid ingots or cakes. These would be ground into powder when needed, sometimes as loose powder, ready for mixing with binders. The powder could be mixed with water for fresco painting, mixed with egg or gum arabic for panel painting, mixed with wax for encaustic painting, applied to wet plaster for murals. The applications were endless. Architectural decoration, tomb paintings, sculpture coloring, ceramic glazes, cosmetics, even early forms of glass. Egyptian blue was everywhere. For over 3,000 years, from roughly 3000 BCE to the Roman period, Egyptian blue dominated. No other synthetic blue existed, no comparable alternative. This was the blue, and then it stopped. Around the 3rd or 4th century CE, production ceased. The Roman Empire was declining, trade networks fragmenting, technology being lost. The formula for Egyptian blue disappeared. For nearly 2,000 years, nobody knew how to make it. Fast forward to the 19th century. Chemists and archaeologists studying ancient Egyptian artifacts were puzzled by this blue pigment. Chemical analysis showed it wasn't lapis lazuli, wasn't azurite, wasn't any known natural mineral. What was it? Various theories emerged. Some thought it was a special type of glass. Others suggested unknown mineral sources. But chemical analysis revealed the composition: calcium, copper, silicon, oxygen. That meant it was synthetic, man-made. But how? In 1814, Sir Humphrey Davy studied Egyptian blue samples. He was one of the first to recognize it as an artificial pigment. He analyzed its composition, proposed theories about its creation, but he couldn't recreate it. Through the 19th century, various chemists attempted synthesis. Most failed to produce the correct color or crystal structure. The challenge: achieving the exact conditions needed for proper formation, temperature control, ingredient ratios, heating duration. Finally, in the late 1800s, chemists succeeded. By carefully controlling temperature and composition, they recreated Egyptian blue. The ancient formula was recovered. Modern chemistry could now explain what the Egyptians had discovered empirically. Calcium-copper silicate forms through solid-state reaction at specific temperatures. The copper gives the blue color. The silicate structure provides stability. The Egyptians had figured this out through observation and experimentation. Without modern chemistry, without atomic theory, without spectroscopy, just heat, ingredients, and careful attention to results. But the rediscovery revealed something else. When modern instruments analyzed Egyptian blue more thoroughly, unexpected properties emerged. Properties the ancient Egyptians couldn't have known about. Properties we didn't even understand until recently. 2013. A research team studying Egyptian blue made a remarkable discovery. Egyptian blue exhibits near-infrared luminescence. When exposed to visible light, it emits near-infrared radiation. This isn't just interesting, this is quantum mechanical behavior. Let's break this down. Luminescence occurs when a material absorbs energy and re-emits it as light. Egyptian blue absorbs visible light, particularly red light. The copper ions in the crystal structure absorb photons. Electrons get excited to higher energy states. Then those electrons fall back to lower energy states. When they fall, they release energy as photons, but not visible photons, near-infrared photons. Light just beyond what human eyes can see. This is quantum fluorescence. The behavior is governed by quantum mechanics, the physics of the very small. Electrons in the copper ions exist in discrete energy levels, quantum states. When photons hit them, electrons jump to higher states. When electrons drop back down, they emit photons of specific wavelengths. The wavelength depends on the energy difference between quantum states. For Egyptian blue, that wavelength is in the near-infrared, around 900 nanometers. The ancient Egyptians created a quantum material. They didn't understand quantum mechanics. That wouldn't be discovered for another 5,000 years. But they created a material with quantum properties. Unintentionally, empirically, through experimentation. But here's what's truly remarkable. This property is incredibly useful for modern technology. The near-infrared emission is bright, very bright. Egyptian blue's quantum efficiency, the ratio of emitted photons to absorbed photons, is remarkably high, about 10 to 12%. That's competitive with some modern fluorescent materials. And it's stable. It doesn't degrade. It doesn't photo-bleach. You can excite it repeatedly. The emission doesn't diminish. This makes Egyptian blue useful for modern applications. Near-infrared light has special properties. It penetrates biological tissue better than visible light. It's scattered less by particles and surfaces. It's invisible to the human eye, but easily detected by cameras and sensors. Potential application 1. Biomedical imaging. Near-infrared fluorescent dyes are used in medical imaging. They help visualize tissues, blood flow, tumors. Egyptian blue could be used as a biocompatible imaging agent. Non-toxic, stable, highly fluorescent. Potential application 2. Telecommunications and data transmission. Near-infrared light is used in fiber optic communications. Egyptian blue could be used in optical devices, light-emitting components, signal markers. Potential application 3. Security and authentication. The near-infrared emission is distinctive, easily verified but difficult to fake. Egyptian blue could be used in security inks, watermarks, authentication markers. Hidden marks invisible under normal light, but clearly visible under infrared. Potential application 4. Solar energy. Near-infrared wavelengths represent a significant portion of solar energy. Materials that manipulate near-infrared light could improve solar cell efficiency. Egyptian blue's properties are being studied for photovoltaic applications. Potential application 5, laser cooling. This is more exotic, but real. The quantum properties of Egyptian blue could potentially be used in laser cooling applications, using light to cool materials to very low temperatures. Modern researchers are actively studying Egyptian blue, not as an ancient curiosity, as a functional material for 21st century technology. Papers published in Nature, Advanced Materials, Applied Physics Letters, scientists exploring its quantum properties, its photonic behavior, its potential applications. The ancient Egyptians created a material we're still discovering uses for. 5,000 years later, we're finding new applications. For a pigment invented in the Bronze Age. Think about that. The ancient Egyptians created Egyptian blue empirically. They didn't understand quantum mechanics. They didn't know about electron energy states. They didn't understand crystal structure at the atomic level, but they understood what worked. They knew certain ingredients, in certain ratios, heated to certain temperatures, produced this blue. They knew it was stable, permanent, beautiful. They knew it could be applied to various surfaces, mixed with different binders. They developed a sophisticated understanding of its practical properties. But the underlying science? That would remain hidden for millennia. The quantum properties of Egyptian blue depend on its crystal structure. At the atomic level, Egyptian blue forms a specific crystalline arrangement. The copper ions sit in particular positions within the silicate framework. This arrangement creates the electronic structure that gives Egyptian blue its color and its fluorescence. The blue color itself is quantum mechanical. Visible color comes from electron transitions. The copper ions in Egyptian blue absorb red and yellow light. Electrons jump to higher energy states when these photons hit them. Blue and green light aren't absorbed. They're reflected or transmitted. That's why we see blue. The near-infrared emission is also quantum mechanical. Different electron transitions, different energy states. When red light is absorbed, some of that energy is re-emitted as near-infrared. This is anti-Stokes emission. The emitted photons have less energy than absorbed photons. The difference goes into heat or other processes. The stability of Egyptian blue comes from its crystal structure. The silicate framework is robust. The chemical bonds are strong. Egyptian blue doesn't react with air, doesn't degrade in sunlight, doesn't dissolve in water, doesn't oxidize easily. This chemical stability is why 5,000-year-old Egyptian blue still looks fresh. The ancient Egyptians discovered all this through observation. They didn't need quantum mechanics to know Egyptian blue was special. They just needed to observe, to experiment, to remember what worked. This is empirical chemistry, not theoretical, not based on underlying principles, based on observation, trial and error, accumulated knowledge, the same approach that led to bronze, to glass, to ceramics, to metallurgy, practical chemistry, driven by need and curiosity. Egyptian blue wasn't the only pigment ancient Egyptians used, but it was the most innovative. They used natural pigments extensively. Red and yellow ochres, iron oxide minerals, black, carbon from soot or charcoal, white, gypsum or calcium carbonate, green, malachite, a copper carbonate mineral. But these were all natural, ground from minerals, used as found in nature. Egyptian blue was different. It was synthesized. created through chemistry. The Greeks and Romans adopted Egyptian blue. They called it ceruleum, meaning sky blue. Used it extensively in frescoes, mosaics, architectural decoration. Pompeii's walls, many painted with Egyptian blue. Roman glass, often colored with Egyptian blue, but they never developed an alternative. For over 3,000 years, if you wanted synthetic blue, Egyptian blue was the only option. The next synthetic blue wasn't invented until 1704. Prussian blue. Discovered accidentally by a German dye maker. A different chemistry, a different process, but finally an alternative. Ultramarine, the other famous blue, was natural. Ground from lapis lazuli, expensive, rare, more valuable than gold. A synthetic version wasn't created until 1828. Egyptian blue predates all of them. The first, the original, the pioneer. 5,000 years of history. Today, we can make Egyptian blue easily. We understand the chemistry. We have precise temperature control. We have pure ingredients. Modern production is straightforward. Artists and conservators make small batches. For restoration work, for historically accurate reconstructions, for artistic use, the pigment is commercially available. You can buy it. Small companies produce it. Specialty pigment suppliers stock it. But it's not common. There are easier, cheaper ways to get blue pigment now. Synthetic ultramarine, cobalt blue, phthalocyanine blue. Egyptian blue is a niche product, historical interest, specialized applications. Except now, the quantum properties have changed that. Researchers are producing Egyptian blue for scientific study, for potential technological applications, for materials science research. The ancient pigment has become a modern material, being studied in cutting-edge physics labs. For 21st century applications, 5,000 years after it was invented. So what's the truth about Egyptian blue? It's real, it's documented, it's still used today. The first synthetic pigment in human history, created 5,000 years ago through empirical chemistry, used extensively throughout ancient Egypt and the classical world, then lost for 2,000 years, rediscovered through modern chemistry. And then we found something unexpected. Egyptian blue has quantum properties, near-infrared luminescence, quantum fluorescence, properties we didn't understand until the 21st century, properties that make it useful for modern technology. The ancient Egyptians created something remarkable. Not just a beautiful color, not just a stable pigment, a quantum material. With applications we're still discovering. They didn't understand the quantum mechanics. They didn't know about photons or electron energy states, but they didn't need to. They observed, they experimented, they refined. They created something that worked, something beautiful, something lasting. And 5,000 years later, we're still learning from it. Modern scientists studying an ancient pigment, finding new uses, new applications, new understanding. Subscribe to Pharaoh's Legacy for more discoveries about ancient Egyptian science and technology, because the ancients weren't primitive. They were observant, innovative, creative. They solved problems, they invented solutions, and sometimes those inventions were more sophisticated than we ever imagined. Egyptian blue isn't just history, it's chemistry, it's quantum physics, it's modern technology, all in a 5,000-year-old color.